Welcome. In this video I'm going to show you how you can determine the Wilcoxon signed rank distribution using R. I'm using Jupyter Notebook, but the codes will also run in, for example, RStudio. This video will focus on how to obtain this distribution using the enumeration method, which is quite a long method actually. If you're interested more in the concept about the distribution, I have a separate video on that. I also have a separate video on how to actually obtain this using my own stickpen R library, for example, which just has a simple function to actually obtain the distribution. But in this video, I'm going to do it the hard way by using enumeration. So let's say we have n data points, and therefore the ranks can go up from 1 to n. Some of these might have been positive differences, some of them might have been negative differences. In total, there are therefore, because we have two options, either positive or negative, there's 2 to the power of n different ways we can actually split these ranks between positive and negative. In each of these possible splits, we can then sum the ranks for the positive and the ranks for the negative differences separately. So let's begin with setting our sample size of 6. And to get all the possible permutations that we can have of each of the ranks distribution, we can use 0 for negative and a 1 for a positive. And then we can simply use this expand grid function from R. And that gives us a long list of all the possible variations to the t is just a transpose of that grid. So for example, here we have 1, 1, 0, 0, 0, 0. That means the first value is used and the second one, so a rank of 1 and 2. And if, for example, we have something like this, it would mean that ranks 1, 2, 3, and 5. 1, 2, 3, yeah, and 5 were negative differences, and the ones are the positive ones. So there should be 2 to the power of n possible options, and indeed that's the case. Alright, now we want to sum the positive ranks from each of the possible permutations by simply multiplying the distribution with the ranks. So if we store the ranks 1 to n in a separate list, so then we get the ranks 1 to 6, and then we multiply each of these with the permutation. So basically multiplying each of these with each of these. And we can do that in one go by saying the column sums and then sum up the results. So it's doing all the distribution times the ranks and then actually sum them all up per column. And that gives us a long list of the sum of ranks that are all possible. So our first one has a sum of 0, a 1, 0, 0, 0, 1, 0, 0 would of course be a 1, etc. The maximum, as you can see, is probably 21, and that should also be simply the sample size times the sample size plus 1 over 2. So we can also calculate it immediately, which is indeed 21. Then we can actually look at how often each of these actually occurs, each of these ranks. So we can simply make a table out of it, and this tells me that, for example, a sum of ranks of 9 occurred 5 times. So somewhere in here is a 9 5 times. The probability is then simply to divide each of these frequencies that we have up here by the sum of all of them, which should be still the same as 2 to the power of n. So we can simply then get the probability distribution, and here it is. We can visualize these if you want. So it looks actually like this. As you might notice, it's symmetrical. And the final check should of course be that the sum of all of them should be 1. Now we had, for example, a sum of ranks of 3. We can find the probability by simply looking it up in the table we had earlier, and that's about 3%. For the cumulative one, we simply add all of them up until that point. I'm adding 1 because in our array star and list start at 1. So we want to include one more, and we get to 7.8% is the chance of having a sum of ranks of 3 or less if the sample size is 6. And that's how you can come up with the Wilcoxon signed rank distribution. I hope this was helpful, and thank you for watching.